Welcome back, everybody, to this second video of week 7 in our calculus course. Last time we looked at implicit differentiation. That was kind of almost the last little bit of theoretical, or should I say more calculation-oriented part of the course. We're entering today a part that is called the applications of derivatives, and the first one of them is actually called graph sketching. So that's a more applied part where we actually see how calculus can be used to perform different tasks. So I've divided this into three parts. So increasing and decreasing function is the first one. So part one, increasing, decreasing functions. I'd like to introduce this by looking at a graph of a function. So consider the graph of f of x, and the graph of f of x is going to go like something like this. So x-axis and y-axis. And let's actually have something like this. So maybe something like that, something that actually goes up, reaches some sort of a top point, and then actually is going to come down somehow to give us this. And then from here, I'd like to do something that many of you will recognize as a point of non-differentiability, as a cusp. So I'm going to go sharp and then down like this, so you can see that this is a point where the function has no derivatives. Yes? Okay, so we're going to do that, and then we're going to actually go back up like this, and then like that. And then maybe I should actually do less straight lines and do something perhaps more curvy. Let's have another of these weird points like that. So that is a strange looking graph of f of x, yes? All right. So sharp point, another sharp point, because smooth and then boom, change in orientation. Another one here and another one here. So this graph is actually full of strange points. Let's have a couple of points here. Let's put like A here, B, C, D, E, F, G, and H. That should give us plenty to kind of do the analysis we need to do on the parts of this graph that are actually increasing and decreasing. So let us begin with something fairly intuitive. Okay, by intuitive I mean we all know what increasing, decreasing means. Increasing means it's going up, and decreasing means it's going down. So I'm going to say that f is keyword increasing, and by increasing I am going to actually have this symbol to mean increasing, so an arrow oriented upwards, that's going to mean increasing. So f is increasing on what interval? That means that f is actually going up on what interval? Well, from A to B, as I move from left to right, the curve is going up, 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 up until B. So definitely the interval AB is an interval for which f is increasing. So I'm going to put open intervals here. What else? Is it increasing on B to C? No, because now from B to C, going again from left to right, the curve goes down. But then it goes back up again from C to D. And then from D to E it goes down. And then from E all the way up to F. From E all the way up to F. It actually goes up again. And then from F to G it goes down. From G to H it doesn't seem to be going neither up or down. And then from H to infinity it basically goes all the way down. So from an intuitive point of view, we say that the graph of f is increasing simply when it goes up. I'll give you like a formal definition in a minute, but we're still at the intuitive level. F of x is decreasing. F of x is decreasing, an important notion. And of course, the symbol is the arrow going down. So arrow going down means decreasing. Decreasing means as I move again from left to right, the graph goes down. So we saw that from A to B the graph goes up, and then it goes down from B to C. So B to C. Where else? Then from C to D it goes up, but from D to E it actually goes down. So from D to E it went down, from E to F it went up, and then from F to G it went down again. F to G, and then from G to H it actually stayed still. This is actually sort of a plateau. And finally, from H to infinity, the graph continues to go down. So just to label the different intervals on this graph, where the function increases, decreases, it's a simple thing. You just look at where the graph goes up, it's increasing. When the graph goes down, it's simply decreasing. So if you want a formal definition, I can give one to you. So we can actually say, so definition, f is increasing, f not if, f is increasing if f of x2 is greater than f of x1 whenever x2 is greater than x1. That is to say, you could have here, for example, an x1, and you could have here, for example, an x2. So you can see that x2 is larger than x1. So here, what we're saying is that if f at x2, that point, is larger than f at x1, that point, right? This is higher than that on the y-axis. Then we can actually say that the function increases, and it does, from C to D. So that's one way to express an increasing function. And similarly, f is decreasing if the opposite happens. F of x2 is less than f of x1 whenever x2 is larger than x1. We could actually see that over here. So for example, again, this is x1, this is x2. Look at f of x1 right here. So it's a high value. And look at f of x2 right there. It's a smaller value. So f of x1 is larger than f of x2. So f of x2 is actually less than f of x1, resulting in a curve that actually goes down, and that means that it is decreasing. Good, 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 good. Okay, so let's see if we can show something perhaps a little more analytical with some x's in it. So we'll get rid of this. Okay, so the next thing I want to do is, again, consider a graph, because everything in this chapter is really about graphing, right? So this time I'd like to actually use maybe some sort of an online tool like Desmos to help me graph the following function. So consider the graph, consider the graph of f of x is equal to x4 over 4 minus 2/3 x3 minus x2 over 2 plus 2x minus 1. All right, well, that's like a 4th degree curve, right? So double quadratic, x to the 4. And these are not necessarily easy to sketch, so we're going to use like software from the internet to sketch this, and we're going to get something like this. So y-axis and x-axis, and we're going to actually show the graph here. So basically, change colors. Something like this is what we would get, obviously with some specific numbers. Namely, I do believe we have, change colors again, I do believe we have here -1, and I do believe we have, what else? 1, so basically this corresponds to that point. This corresponds to that point. This corresponds to that point. So -1 and 1 and 2. So if you can verify this, if you plug this into a software, you're going to get a graph like this, where this continues to go up on both sides of the thing. Okay. So what can we see on this? We can see that. Okay, let's do the analysis of where f is increasing and f is decreasing. F goes up on what interval? -∞ to -1, clearly the graph goes down. But after -1, it reaches a low point and it goes up again until 1, right? So I'm going to say from -1 to 1. What else? So -1 to 1 it goes up, 1 to 2 it goes down, and then goes back up at 2 to infinity. So we could say this, 2 to infinity. And f goes down on -∞ to -1. And then it goes back up, and then it goes down from 1 to 2, and then it goes back up to infinity again. So the graph is actually quite self-explanatory. What I'd like to introduce here is a way to arrange this in a tabular form. So table form, what could we actually have here? Well, in a table, I can organize my work in a very clear fashion if I do it this way. So I'm going to go here with a two-level table. So x on top and f of x below. And I'm going to go from -∞ to +∞. And here I'm going to put key numbers. I call them breakout numbers. Numbers that actually determine where the intervals stop being one way and start being another way. And we can see that these key numbers on the graph are -1, 1, and 2. So it's like I'm having here intervals. Okay, so these actually stand for -infinity to -1, then -1 to 1, then 1 to 2, and then 2 to infinity. And what I can do is I can put arrows in the line for f of x. That's going to tell me if I'm going up or if I'm going down. So from -infinity to -1, I am decreasing, right? From -infinity to -1, I am decreasing. Then from -1 to 1, I am increasing. Then from 1 to 2, I am decreasing. And from 2 to infinity, I am increasing again. Interesting indeed. All of this is an analysis that could have been performed in high school. There is no calculus in there at all. Perhaps you've done this in high school somewhere in Sec 4 or Sec 5. So now what's going to be interesting is to see if there is a connection to calculus, and of course there is. So let's keep an eye on this and let's try to see what happens when I take the derivative of this function. So all right, let us rewrite what f of x is. So let me rewrite it over here. F of x is what? x4 over 4 minus 2 over 3, x3 minus x2 over 2 plus 2x plus 1. This is what we had in the previous page. I will be interested in figuring out f prime. Okay, how do I calculate this? Well, we're kind of semi-experts on this, so we can actually do this relatively quickly. This is 1/4 x4, so I'm going to pull the 1/4 and derive the x4. I'm going to pull out the 2/3 and derive the x3. I'm going to pull out the 1/2 and derive the x2. I'm going to pull out the 2, derive the x, and I'm going to derive the 1. So basically what I get here is 1/4 times 4 x3 minus 2/3 times 3 x2 minus 1/2 times 2x plus 2 plus rien, zero, niente, nada. Forgot my prime here. The derivative of a constant is 0. Cleaning this up a little bit, this is just x3. Oh look, these 3 also cancel, so minus 2x squared. Oh, look at these 2's cancel, so that minus x plus 2. And of course I'm not going to put down the 0. Lovely. I could stop here, but suppose it says ds, do simplify. Let me see if I can simplify this. How would you simplify this 4-term expression? What would you do? Oh, are you thinking of factoring out 2 by 2? That's actually a pretty good idea. What can I take out from the first 2 terms? What's common to x3 and minus 2x squared? I can take out an x squared. What will I be left with? X minus 2. What can I take out from the last 2 guys? Well, minus x plus 2 don't seem to have a lot in common, except perhaps a minus 1. If I factor out a minus 1 from minus x plus 2, will I not get x minus 2? Now I have the same term, so I double factor, and I have x minus 2 times x squared minus 1. Oh, difference of squares. So I can really, fully, completely simplify this derivative by writing it as x minus 2 times x minus 1 times x plus 1. Good job. Good job, good job. Now, all this, basically, this is 0. This is equal to 0 when, what are the values that actually make this expression equal to 0? Certainly, when the first bracket is 0. So, x is 2. This could be made equal to 0 as well, or minus 1, 1 or minus 1. These are the three values that, if I plug them back in, one at a time, I'm going to get 0 here. Why does that matter? Because I want to show you something pretty cool. Remember that little table we did in the previous whiteboard, where we actually had like x and f of x? Let me do a similar one, but for x and f prime. I think I need a little more space than that. So let us go from minus infinity to infinity, and let us put those guys there in order from least to largest. So the smallest one is clearly minus 1, and then 1, and then 2. So minus 1, and 1, and 2. Let us subdivide this into intervals. And let's take a look at something very, very interesting. This is where we're actually going to make a link between things that's going to be useful for the next couple of weeks. Look at this long interval from minus infinity to minus 1, right? You've seen it before in the previous graph. Now, I want to take a look at this from the perspective of what happens if I pick a number between negative infinity and negative 1, any number, and I plug it into f prime. I'm looking here to put some signs, like plus or like minus, okay? So if I take here any number between minus infinity and minus 1, let us say I pick, I don't know, minus 3. Ugh, not good. Let us say that I pick minus 3. I would like to put minus 3 into f prime, okay? Let's take a number between negative infinity and minus 1, like negative 3, and put it here into f prime. Where is f prime? This is f prime. This is the factored version of f prime. Okay, let's take a moment and let's figure out f prime of minus 3. Here we go. Let's put it here. What's minus 3 minus 2? Minus 5. Minus 3 minus 1? Minus 4. Minus 3 plus 2? What's the outcome of minus 5 times minus 4 times minus 2? Well, the outcome is minus 40. Do I care about the 40? No. Do I care about the sign? Yes. F prime is negative on the interval negative infinity to minus 1. Let us pick a number here between minus 1 and 1. What could we pick? 0? Good idea. F prime of 0. Let's put it here. 0 minus 2, that is minus 2. 0 minus 1, that is minus 1. 0 plus 1, that is 1. Final answer, positive 2. I don't care for the number, I care for the sign. This is a plus. Pick a number between 1 and 2, pick 1.5. F prime of 1.5. F prime of 1.5. Yo, 1.5 minus 2, minus 0.5. 1.5 minus 1 is 0.5. And 1.5 plus 1 is 2.5. So what is that equal to? That is actually equal to 0.625 with a minus. Put a minus where? Here. Put a minus right here. Again, the number is not important, but the sign actually is, because it's a minus times a plus times a minus. Here's a minus. Finally, pick a number between 2 and infinity. Say 3. What is f prime of 3? 3 minus 2, uno. 3 minus 1, duo. And 3 plus 1, quattro. The answer is 8, which is a positive number. And then we have this table here. So minus, plus, minus, plus. And that is interesting, isn't it? Because of the table we had before, this is actually linked to the fact that f is increasing or decreasing. Oh, that's kind of nice, huh? That's kind of nice. So let's get rid of this and let's take a look at the two tables that we had. So I'm just going to keep that for one moment, and I'll get rid of it in 1 second. So pulling together both tables, pulling together both tables, what I actually have is this. So here's an x, and here's an f of x, and here's an f prime of x. Right? Minus infinity to infinity for my x's. You remember the key numbers were -1, 1, and 2. And basically I'm just recopying here what we have done in the previous whiteboard. Here I actually had arrows going down. So we had arrow going down, arrow going up, arrow going down, and arrow going up. While the signs that we had were negative, plus, negative, and plus, like this. So I can get rid of this now. So you can probably see the connection now between f and f prime, right? The connection is quite clear in terms of if f prime is negative, then f is increasing. And if f prime is negative, f is decreasing, f prime is positive, f is increasing, and so on and so forth, right? So we have this as a result. We'll put that in blue. So our result at the end of the day actually reads like f. So it's a two-part result. F prime at c greater than 0 means f is increasing around c. Right? So if the derivative at a point is positive, we link that to the fact that f is increasing. Similarly, if f prime at c is negative, what will this mean? It means that f is decreasing around the point c. So that's the result we can actually draw from this whole thing. Visually speaking, it's not difficult to convince ourselves that on a graph that is increasing, here I drew f that is increasing. If I draw a tangent line here, and I draw another tangent line here, all of these lines have what? The same slope, right? A is positive. The slope of the tangent line of these orange lines, they're all oriented in such a way that they're positive. And that means that because they're tangent lines, it means that f prime greater than 0. And if I draw a function f that is actually decreasing like this, and I draw some tangent lines, yes, so here's a tangent line right here. That's supposed to be a line. My God, that is supposed to be a line. Do a better job. Tangent line. Draw another one here. I'm having trouble drawing straight lines. But you can see my point. Those tangent lines, they're oriented in such a way that they will be negative. And that is associated with, of course, A, the slope of the tangent line is the derivative. We know that. Good. All right. So, an important result, we can box it and actually use it in solving the last example of the day. So, important result. F prime positive means f is increasing around a point, and f prime negative means it is decreasing. So, let's do one last quick example to conclude this lecture. The first one on graph sketching. And the problem will actually read like this. So example, find all intervals where f is increasing and decreasing, where f of x is actually given by 2x3 minus 3 x2 minus 36x plus 6. So I could go to Desmos and I could actually sketch this, and then I would have to read the answers. But I'd like to use what we have learned today. That is, when f prime is positive, the function is increasing, and when f prime is negative, the function is decreasing. So let me look for f prime. Yeah, let's go quickly over this. This is 6x2 minus 6x minus 36. Clearly, I can take out a 6. X squared minus x minus 6. Oh, that can be refactored, yes, into x moins 3 and x plus 2. This is equal to 0 when x is equal to what? Well, the 6 does not contribute, but here, this bracket will be 0 when x is 3, and this bracket will be 0 when x is minus 2. So let me do my table with those two numbers, and I will have what I want. So let me do my table with only two values in it. So I have minus infinity to infinity. And the two numbers that I'm going to put on my interval here are minus 2 and 3. Remember to put them in order from least to largest, because this actually symbolizes a real line. So I'm going to have an f here. I'll put a prime. And I'll put an f like this. Doesn't really matter which one goes on top and which one goes at the bottom. And then I do my thing. I pick a number. I pick a number between negative infinity and minus 2. Let's pick minus 4. Okay? Minus 4 I'm going to put into f prime. So f prime of minus 4. Where is f prime? Here is f prime in its simplified version. So 6 times minus 4 minus 3 minus 4 plus 2. I'm going to get right down to the jugular here. I don't care for the number, but I do care for the sign. Un plus, un moins, un moins. Two minuses and a plus, that's going to give me a plus. It's something positive. Okay, so let me put like my divisions here, which I should have done before, so that I have here a plus. Let's pick a number between -2 and 3. Let us pick 0. So f prime of 0. 6 times 0 minus 3 times 0 plus 2. A positive, a negative, a positive. Finally, pick a number here between 3 and infinity. Why don't we take 5? So 6 times 5 minus 2 times 5 plus 2. Here everything is positive. Now what do we conclude? If that's a positive, that's a negative, and that's a positive, we may conclude that the function is increasing in this interval, decreasing in this one, and increasing here. So I can draw my conclusion here, and I can say that f is increasing on minus infinity to minus 2 union 3 to infinity. And I can also say that f is decreasing on minus 2 to 3. We keep those intervals open. All right, so that's enough for one day, I believe. So I will see you in the next video with the continuation of this material. I wish you well. You take care for now.